Good morning. In the past two lessons, we studied the k nearest neighbor or the KNN algorithm for classification. We also studied the probabilistic classification methods. In this lesson, our primary focus is on decision trees for classification. We'll first explore a little bit of background about decision trees. We'll take a very simple example and then we will move on to the movie script example. We will see how the classification works at a theoretical level using the movie script example. We'll implement our Markdown code for the credit default example. In the credit default example, we will be trying to predict whether a customer is likely to default on his or her loan, and we would use decision trees to make that prediction. For the decision trees, we will implement one of the very popular decision tree algorithms called the C5.0 algorithm. And just like before, we will be implementing all this using our Markdown code. This is a scenario that most of you are familiar with. You got multiple job offers and you are trying to make a decision on which one to accept. You are looking at some criteria for making that decision. One of the criteria is the salary. The second criteria is the commute time. So the first level of classification occurs based on salary. So if you look at the top of the decision tree, that's called the root node. At the top, you do see that the salary should be at least $50,000. If the salary is at least $50,000, is it yes? If it is yes, you go through the branches on the left side of the decision tree. If it's not, you go to the branches on the right side of the decision tree. If it's not, the decision is simple. You are not going to accept this offer, so you decline this offer. So this green oval decision of declining the offer, you make it immediately based on salary alone at this stage. If the salary is indeed at least 50,000, then you go down this path. The next criterion for you for the decision is what is the commute time? If the commute time is not more than 1 hour, you are willing to consider this offer. If the commute time is more than 1 hour, you will decline the offer as shown in this green oval box. If the commute time is not more than 1 hour, you use the next criterion. Maybe you are a coffee lover. Whether the job offers free coffee or not, that's one of the criteria that you would use in the end to make decisions about the job offers. If they offer a free coffee, you come to the last level and you accept the offer. If they do not offer free coffee, you decline the offer. So you have exhausted three different classification criteria that you had. One of them is the salary. You started with the salary. And the next one is the commute time. You looked at the commute time. And the third one is free coffee or not. Based on these three, you made a decision tree on whether you would accept a job offer. You have classified all possible outcomes on whether to accept the offer or to decline the offer. The green oval shaped symbols here, they represent whether you accept or decline the offer, and they are called the leaf nodes. Once you have reached the leaf nodes, the decision tree ends at that point. One of the heuristic methods to construct decision trees is called divide and conquer. It is also called recursive partitioning because what you do in this method is to divide the data into subsets. First, you might divide the data into two subsets, just like we had done in the previous example related to accepting a job offer. You take each subset and you further subdivide it into smaller subsets. You continue this process until you stop the algorithm. So one of the questions that you may have is, when do we stop at a node, or when do we stop the algorithm? The recursive partitioning continues until one of these three criteria that are shown here is satisfied. For example, if you reach a node and if all the examples at that node belong to the same class, you don't have to keep subdividing that node. On the other hand, if there are no remaining features, there are no remaining criteria for you to distinguish among examples, you could stop the recursive partitioning at that point. The third way to stop the recursive partitioning algorithm is if the tree has grown to a predefined size limit. You can specify the size limit for the tree, and based on that, you could stop building the decision tree if it reached that size limit. Our next example is going to build a decision tree on whether you should move forward with producing a screenplay that is pitched to you by promising new authors. Let's say that you are working at an executive, you are a hotshot executive, and everybody is coming up with these cool screenplays they say that would result in a big hit for the studio. Should you be accepting this or not? Given that you are a data analytics enthusiast, you decide to develop a decision tree algorithm to predict whether a potential movie would fall into one of these three categories: critical success, mainstream hit, or box office bust. To construct the decision tree, you reviewed the 30 most recent releases from your studio, and you found out that the budget and the number of A-list celebrities that are starring in those films, they are the two most important criteria for determining the level of success. So you took those 30 releases, and in this example, we have 10 of them neatly grouped into critical success, 10 of them into mainstream hit, and 10 of them into box office bust. The purple circles are box office bust, the triangles are the mainstream hit, and the rectangles are critical success. You made a scatter plot of this data with estimated budget on the x-axis and the number of A-list celebrities on the y-axis, and you placed each of these data points on this scatter plot. For you to visualize the decision tree, the first split that you are going to make is based on the number of A-list celebrities. Is that high or low? You can determine a number and you can use that number. The first split on this graph is made using this dashed line. By the way, this is called the axis parallel split. In other words, the line that you draw to split is going to be parallel to either the x-axis or the y-axis. In this case, it is parallel to the x-axis, the estimated budget, and it is based on the number of A-list celebrities. So you made the first level of split, and now we are going to go ahead and make a second level of split. The second level of split is based on budget, whether the budget is high or low. Once we make the budget based split, the split 2 shown as a dashed line here, we have neatly grouped most of our data points into homogeneous groups. For example, in this group or in this subset, we have critical success. In this group here, we have only mainstream hits or mostly mainstream hits with one critical success. In the group below, we have mostly box office bursts. So we are about to make our decision tree, and our decision tree looks like this. At the root node, we have 10 of each, and then we make the first level of split based on the number of celebrities. If the number of A-list celebrities in starring roles is low, we can safely classify that as a box office bust. You know why? Because the box office bust in that category based on our data is 10 out of 12. We have 10 out of 12 observations and that are falling under box office bust. If the number of celebrities is high, we have critical success as 9, mainstream hit as 9. So we need another criteria to classify these two. So the next criteria we use in this path is the budget. If the budget is high, we know that the mainstream hit is 9 out of 10, which is great. So we classify that as mainstream hit. If the budget is low, then it's falling under critical success 8 out of 8, and we classify this as critical success. So in sum, if the number of celebrities is low, most likely we are going to classify that as a box office bust. If the number of celebrities is high and the budget is high, it would most likely result in a mainstream hit. Otherwise, it's going to be critical success. Next, we are going to look at the credit default example. In this example, we have 1,000 observations on 17 different variables. You can see that because we have so many variables, it is very tough for us to use a decision tree and construct a decision tree manually. This is where we need to use data analytics programs such as R or Python to complete this exercise. So in this example, we are going to develop our Markdown code on predicting whether a customer is likely to default on his or her loan. For these 1,000 observations, we have 16 different features that help us make the decision. And we are going to predict the last one here, shown in red, the default, whether the customer is likely to default yes or no, based on these 16 different features or variables. The different features for each loan or each observation are checking balance, how much checking balance that the customer has. We use this as a factor with 4 different levels. You know how factors work in R from a previous lesson. We also look at the months of loan duration. We look at the credit history as a factor, the purpose for this loan, whether it is a business loan or whether it's a car loan or whether it's mortgage and so on and so forth. We look at the amount. We look at the amount of balance that they have in their savings account. The employment duration is another factor that we would use. What percent of the customer's income is this loan amount? The number of years at the current residence, that is another feature we look at, the age of the customer, and so on and so forth. In terms of the R code, we are going to look at the code features or some lines of code. I want you to focus on how to read the data file, which you already know from previous lessons. I also want you to be able to split the data into training and testing sets. We'll review the code for building a model. We'll see the results of the decision tree, or we'll visualize the decision tree. We can see pictures of different nodes. In addition, we'll test the model. We'll see what the false positives and false negatives are, and we'll see how to improve the decision tree model, the basic decision tree model that we have constructed. So here is the data file that we are going to use for predicting whether a customer is likely to default on the loan. So we have 1,000 observations and 16 different uh, criteria based on which we are going to make this prediction. And the last one, the 17th column, is the actual predicted variable, default yes or no. These 1,000 observations is from past data. That is the reason why the default value is already filled out. In terms of the R Markdown code, you are familiar with this. So with these chunks of code, first we are going to load these packages. One of the packages is impute TS that we have used in the past for dealing with missing data. We are not going to use that in this example, but I just want you to be aware of the importance of this package. In step one, we have to collect the data. We have already done collection of data for identifying the risky bank loans. In step two, we are going to explore this data. On line 54, we read the CSV file containing this credit data. The resulting data frame, we are calling it as credit. We explore that data frame using the string method str of credit. We look at the two characteristics of the credit data on line 58 and 59. What are those two characteristics? The checking balance and the savings balance. We're also going to use the summary method to look at the months of loan duration, how long the applicants are taking the loans for, and also the amount. Please note that default is the class variable, yes or no. And on line 66, using the table method, we find out more about the default variable. Line 68 uses a random number generator. We are using an older random number generator, but we had seen other random number generators in the past as part of this course. So you could use any random number generator that you choose. In line 69, we set the seed so that we could reproduce the results that are produced by this code. Line 71, we are generating about 900 indices. How do we generate that? We call the sample method. The sample method is going to generate 900 random indices that we are going to store in train underscore sample. Once we have that, we are going to split our data frame into the training data frame and the testing data frame. The training data frame is called the credit underscore train, and the test data frame is called the credit underscore test. For the training data frame, we would use the 900 indices that were generated on line 71. We use that from the credit data frame. We take that as training data frame. For the testing data frame, we take the remaining one as indicated by this minus train underscore sample. So the remaining indices are the ones that we are going to use for the testing data frame. We are going to check the proportion of the class variable for both the training sets and the testing sets. It is best if the proportions of the class variable, in this case the default percentages, are similar between the training set and the testing set. That's what we are going to check in lines 80 and 81. The decision tree, the simplest of decision trees that we can build, is shown in line 86. Once again, we are going to use the model C5.0, the C50 algorithm, 5.0 algorithm that is available for us. And the way this call works is we are going to use the training data, all the variables in the training data except variable 17. We have to exclude variable 17 because variable 17 is the one that we are predicting for the model. The variable 17 is the default, and that's what we are predicting, and that's what we supply as the second parameter for this credit model. Once this call is successful, we have used the 16 for the first 16 variables to predict. the 17th variable, the default, and that model is available for us in the credit underscore model. The decision tree can also be plotted in R, and we are going to use the plot method to plot this. But I do want you to give you another package called Party Kit. If you use this package, if you install this package and you use this package, you can plot individual nodes of the decision tree. In this case, I'm using the credit model, and I'm also going to get my tree 2. Using this my tree 2, I can plot, for example, node 2 or node 33 of the decision tree. I'm also depicting in line 99 to 103 how to plot different nodes in the decision tree using a for loop. We had seen this in the past, how to use the looping structure in R, and using that we are plotting individual nodes of the decision tree. Once we have the decision tree model, we are going to look at how accurate this model is. We can use the cross table method from gmodels. The cross table method will help us look at the actual default that was given to us as part of the data set and the predicted default, what is predicted by the decision tree model. This helps us review the false positive and false negative rates. One of the key aspects of decision trees, or any model for machine learning for that matter, is to improve the model's accuracy. The C5.0 algorithm, it gives us a way to improve the model accuracy. We can boost the decision tree by increasing the number of trials. We don't have to limit ourselves to just one trial. We can specify the trials as a third parameter in C5.0 call as shown on line 122. We are going to look at how the model would be if we conduct 10 trials on this decision tree. We are calling the corresponding model as credit underscore boost 10. We can review that model's accuracy by comparing it with the test data. So without much delay, let's review this code and let's try to run this code and knit it into an HTML file. Since this is an R Markdown code, that's one advantage we have. We can knit it into an HTML file and review the results of that HTML file. In the next lesson, we will look at how to assign cost to each decision. For example, you might decide that the false positives cost more than false negatives. If we assign cost, we can change the decision tree based on the cost model, and that is also possible using the C5.0 algorithm, and that's what we would see in the next lesson. But for now, let's try to knit this and examine some aspects of what is produced in this HTML file. This is the HTML file produced by knitting the R Markdown code. I want to bring your attention to plotting of different nodes. So for example, we are showing the plotting of node 8 in the decision tree. Remember, we use this code as part of the for loop. We plotted a number of nodes, and one of the nodes is node 8. Node 8 is based on dependence. If the dependence is less than or equal to 1 or greater than 1. If it is less than or equal to 1, then we go to node 9. And at node 9, we are looking at how many years the applicant has resided at their current residence. If it is less than or equal to 3, we come to this node 10. If it is more than 3, we come to node 11. So what do these leaf nodes? The leaf nodes are shown using rectangles. The leaf nodes are labeled as yes or no. The yes means that they are likely to default. That's what our model is predicting, that the applicant is likely to default on their loan. And how many do we have? Node 10 shows that we have 4 observations that fall in this category, and out of those 4, one of them is not likely to default, and 4 of them, or 3 of them, the remaining 3 will likely default. That's why we have 1 out of 4 as 25% or 0.25 at the top, and 3 out of 4 are 75%, 0.75 as yes at the bottom. Similarly, if we come to years at residence greater than 3, we have 5 observations. One of them is likely to default. The other 4 will not be defaulting. That's what is predicted by our model. If the number of dependents is greater than 1, based on the data, based on the model that we constructed, we have 5 observations and none of them will default. Now let's review the accuracy of the model. We use the cross table method to figure out the accuracy of the model, and the accuracy is shown as the output of this cross table method. You can clearly see that the columns here are the predicted default, what our model is predicting, and the rows are the actual default, what is given to us in the data. So the actual default is no, and the predicted default is no, and that is 59. And we have about 100 observations in the testing data. So out of 159, the actual default is no, and the predicted default is no. So those are just fine. On the other hand, the predicted default is yes, 8 times, whereas at the same time, the actual default is no. These are called false positives. That means falsely our model is stating that the customer is likely to default when actually we had witnessed that the customer did not default. So we have 8 such cases, and that is 8% false positive rate. Similarly, if the actual default is yes, but our model is predicting no, that falls under this in this cell. There are 19 such observations. These are false negatives. We actually witnessed a default, but the model is stating that the default did not occur. So as a result, these false negatives are at 19% in our example. So we looked at the false positives and we looked at the false negatives. And what I want you to do before next lesson is to improve this model. We have ways of improving this model. We discussed that several ways to improve the model. So I do want you to go back and apply some of those techniques and come up with a different model that improves the accuracy in terms of reducing the false positives and reducing the false negatives.